In Einstein's footsteps and beyond, zero-index metamaterials offers new insights into the foundations of quantum mechanics. Since the beginning of quantum physics, how light moves and interacts with matter around it has mostly been described and understood mathematically through the lens of its energy. In 1900, Max Planck used energy to explain how light is emitted by heated objects, a seminal study in the foundation of quantum mechanics. Paulson School of Engineering and Applied Sciences, SEAS, and Eric Maser, the Bolkonski Professor of Physics and Applied Physics at SEAS, are re-examining the foundations of quantum physics from the perspective of momentum and exploring what happens when the momentum of light is reduced to zero. At the microscopic scale, an atom recoils when it emits light because of the acquired momentum of the photon. Atomic recoil, first described by Einstein when he was writing the quantum theory of radiation, is a fundamental phenomenon which governs light emission. These metamaterials have a refractive index close to zero, meaning that when light travels through them, it doesn't travel like a wave in phases of crests and troughs. When that happens, many of the typical processes of quantum mechanics disappear, including atomic recoil. In these so-called near-zero index materials, the wave momentum of light becomes zero, and when the wave momentum is zero, odd things happen. Fundamental radiative processes are inhibited in three-dimensional near-zero index materials, says Lobet, who is currently a lecturer at the University of Namur in Belgium. If breaking one of Einstein's rules wasn't enough, the researchers also broke perhaps the most well-known experiment in quantum physics, Young's double-slit experiment. When we modeled and numerically computed Young's double-slit experiment, it turned out that the diffraction fringes vanished when the refractive index was lowered, said co-author Larissa Verchenko, of the Technical University of Denmark. As it can be seen, this work interrogates fundamental laws of quantum mechanics and probes the limits of wave-corpuscle duality, said co-author Inigo Liberal, of the Public University of Navarre in Pamplona, Spain. While some fundamental processes are inhibited in near-zero refractive index materials, others are enhanced. These new theoretical results shed new light on near-zero refractive index photonics from a momentum perspective, said Maser. The research could also shed light on other applications, including quantum computing, light sources that emit a single photon at a time, the lossless propagation of light through a waveguide and more. The team next aims to revisit other foundational quantum experiments in these materials from a momentum perspective. After all, even though Einstein didn't predict near-zero refractive index materials, he did stress the importance of momentum.